Donc, merci à tous. Nous avons donc le plaisir aujourd'hui. I'm going to switch to English because I think it's nicer for the invited speaker to know what I'm telling about him. It's a bit embarrassing otherwise. So it's really my great pleasure to welcome Mete Atatüre. He's from Turkey originally. He's a professor at Cambridge, actually the head of the physics department since 2 years and a half, something like that. He did his PhD in Boston, in the US, and a postdoc then in Zurich, in ETH. And he is now the head of this department. He's a specialist in solid-state quantum optics, I would say, very famous. He leads activities on different systems. So today, I guess, you will talk about quantum dots. Yes. But he's by far not the only system he investigates in terms of solid-state qubits. Including some defects on color centers, as we call them in Diamond. He's also co-founder of a company which is called New Quantum that works on quantum network. You are a scientific advisor there, yeah? And he received multiple recognitions, including a bunch of European Research Council grants. He's a fellow of the I like to say the American Optical Society. Now it's called Optica, but it's really the Society of Optics of the US. He's also a fellow of Institutes of Physics. He receives a Tame medal from the Institute of Physics, right? And he is also elected member at the Academia Europa. So please enjoy and please welcome Mete Atatüre for this seminar.
How about now? Yeah, okay, there we go. All right, I'll put it in my pocket. So it is indeed a great pleasure to be here at the Collège de France. We all know about it. We knew about it growing up, so it's very nice to actually be here among you. So thank you for coming. Thank you for staying after a very nice lecture by Pascale. I'll have an opportunity to not use the board. I'll have the opportunity to talk more hand-wavy about the things that we do, but it relates very much to the lecture, so various topics. So I'll see how I can make those links as we go, trying to tackle some of the challenges that we had over the years. But before I start, this is my research group. This is my team in Cambridge. So any result that I show from us, it's thanks to them, so I wanted to start by thanking the research team who actually do the work together with me. As Pascale mentioned, the group does many areas of research, but there is a thematic overlap. So there are different material systems we study, each with its own challenges and opportunities. But the overlying theme is that we're looking at matter and light interaction, how light and matter interact, to give us some opportunity, some chance to do something interesting. Either to understand that material, that alone is interesting, or to use our understanding and control of that matter properties using light to do something like sensing, for example, and we cover multiple areas. All of these fall roughly under the, I would say, broad umbrella of quantum technologies, but there's a lot of science associated with it. So one thing I'll do today is actually, in the challenge to achieve or progress quantum technologies, there is also a motivation for the pure science part of it, and hopefully I'll motivate that. So starting with, let's see if this works. There we go. So everything that we talk about in quantum is through correlations. So if you don't have correlations, there's not much to do for us. But if you have correlations, you build on correlations, then complexity starts and it becomes more interesting. That's one key element that we're after, one theme that we're after. So if we want to create correlations, there's a very, in fact, it's going to be obvious very soon, there's a very historic way of doing this. You take two uncorrelated entities. I put red blobs So as a physicist, two red spheres or two red blobs are perfectly fine systems. So I take these uncorrelated systems, and what do? I have to get them to interact. So I bring them close. Here's the universal sign of interaction. I bring these two objects close by. They interact somehow. And after the interaction, they go off their way. Right? Now, this setup, if that interaction in particular, let's see if, is this the, oops. Wait, that one? Yeah. So if this interaction is a particular one that creates some correlation between the internal degrees of freedom of the red blobs, I'm not showing you what they are, but let's say that inside the red blobs, they got some properties. If those properties remain correlated afterwards, we could have a situation where the particles far, far from each other have this correlation sustained after that interaction. And this, especially in the concept of quantum correlations, was a problem. 1935, we have this nice paper. Rosen and Podolsky went to Einstein and said, we have this issue, we have this problem with it. And then Einstein got troubled by it as well. And then they wrote this very nice paper called Can Quantum Mechanical Description of Physical Reality Be Considered Complete? It's a question mark. Now, of course, if the answer was yes, they wouldn't write this paper, right? So their claim is that no, because, and then they list all the reasons. And it's the spooky action at a distance that we always hear about as an interesting feature of quantum mechanics was the reason why they wrote this paper to say no. It beats all the notions of local realism. Now, of course, then Niels Bohr, there's a very nice argument back and forth, and it's also nice to read their letters to each other as well. Niels Bohr wrote a second paper called Can Quantum Mechanical Description of Physical Reality Be Considered Complete? Now, of course, the answer is not no, because he wouldn't write that paper. The answer is also not yes. Basically, he's saying that's the wrong way to look at the problem when you're looking at local realism. But it started both of these arguments. And this is, of course, a very popular area of discussion when it comes to quantum physics and the foundations of quantum physics. But I want to highlight another aspect of it. To be able to talk about correlations at a distance, what did they do? They still had to bring the two particles together. The proximity had to happen. So in real life, in nature, when we look at nature, all correlations start because of effectively a nearby interaction. Yes, it's interesting to look at what happens afterwards and with the whole concept of quantum entanglement, but even the fact that you have to bring them together in the first place to create those correlations means that there's a notion called proximity, a length scale, a time scale over given a certain distance between two entities to interact enough to build up correlations between each other. Right? So proximity is key. When we talk about emergent phenomena, we start from the microscopic picture of things interacting with their nearest neighbor or whatever is around them. That interaction collectively leads to interesting, unexpected behavior going forward. So I do not know a physical system that does not rely on building correlations through nearest neighbors, and proximity is essential, except one example that I'll show, and that is if the two red balls somehow are not physically close by, but they share a common radiation mode, an optical mode. So information or energy goes from one red ball to the other. As long as they share this common mode and they can interact through light, then their physical proximity, how close they are or how distant they are, it becomes irrelevant. What matters is that they share this common bus of energy or information. Then the internal degrees of freedom of one red blob could end up being correlated with the other one through this exchange of light, right? So space is no longer an issue. There's one more thing that quantum physics gives us that is odd, and that is those two red blobs don't even have to exchange energy with each other. There's a particular way of doing things. It's called a quantum erasure experiment. In classical world, if you do a measurement, you do it for a purpose. You measure to know. In quantum physics, the concept of a quantum erasure experiment is to make sure you don't know the answer. You make a measurement not to know, but also to make sure no one else knows either. You actually deliberately erase the information fundamentally so no one knows, creates an ambiguity in the right way of doing these measurements to create a correlated state leaving behind. So it ends up being that these two red blobs, never having seen each other directly, no line of sight, can end up being correlated as long as there's a third party that looks at, for example, photons coming from these two entities, or even the probability of photons arriving from these two entities to a third location. So think of the third party, this guy, as a little puppet master. And by doing the right measurement of not knowing, pairwise, they're able to, this third party will be able to weave out correlations between two unrelated red blobs anywhere in space, as long as there is line of sight here and line of sight there, and not necessarily there. So you can imagine if you had beautiful systems, red blobs being the ideal quantum objects, and if you have many of these together, all it takes is weaving out entanglement or correlations pairwise to create a very linked network of these red blobs. A large number of red blobs weaved out not by proximity, not because of the way they're distributed in real space, but because of how we chose correlations to build up, how we chose the pairings should happen. We're redefining, if you're able to do that quantum physics feature, quantum erasure experiment, and you have good enough red balls, coherence-wise, then you can actually weave out phenomena that is independent of topology. You can weave out emergent behavior that doesn't depend on nearest neighbor interactions or doesn't care about proximity. So that I find very interesting. So basically, what I'm saying is, if you have these red blobs linked to light, that's a spin-photon interface, quantum interface, and they are great for quantum networks. But the thing that motivates me as a basic scientist as well is the fact that I might be able to do that one day when the technology is mature enough that we can talk about behavior of matter without the shackles, the chains of topology or where the atoms really lie. So you can think of an abstract space, and you can engineer a completely new matter that way. So on that journey, when we talk about real matter, a good portion of science, physics, still looks at real matter and tries to understand it. And real matter is formed by real atoms and real interactions. Now, we're in this very exciting era where we're deviating from this a little bit. We're in the era where real atoms create a synthetic matter by means of us controlling not how they would show up in nature, but how we would want them to line up in vacuum, in absence of absolute nature. So this is individual atoms in an optical lattice. The behavior of those atoms is very different than if those atoms were in original natural metal form. And their properties are very, very different. It opens us a completely new venue. Here, it is still proximity-based, but it is, again, it's a synthetic matter emerges using real atoms. Another option is using the concept of qubits. The real part is exactly as Pascale highlighted for superconducting qubits. It's an LC circuit with nonlinearity there through the Josephson junction. But if you lump all of that into two states, 1 and 0, and talk about interactions not as real-time interactions, but two qubit operations in the same sense of weaving out a quantum correlation, you can talk about synthetic atoms. Superconducting qubits are not atoms. Synthetic atoms creating synthetic matter through synthetic interactions. It's a very interesting concept. We didn't develop science with this in mind, but these are great venues to explore. And then there's this part, which obviously is going to be a blank if I don't highlight something there, and that is synthetic atoms, real interactions. This is what happens when you have a particular artificial atom, like a qubit, and many of them together, and you put them all in the same chip, for example, like here, but you're not good at controlling it. What happens is they interact with each other without your control. So you don't weave out two qubit interactions, or you don't weave out particular entanglement or correlations. The system naturally evolves. These are these very large qubit systems where control was very limited in the early days, and then something emerges, and we don't even know what it is. So there's an element of quantumness in large chips. That was the early days of superconducting chip array conversations. So that falls into that category. Even synthetic atoms can, if you leave them alone, will create some kind of interactions and lead to new features. So the physical system I'll deal with is going to be relevant to kind of that earlier picture where we don't have exact control of every single artificial or natural atom, but we have an ensemble to deal with, and we have to figure out how to control it. So here's the question that essentially it directs the way that we're doing research for this particular system. Can we capitalize on quantum optics? This is decades, including France, decades of development on understanding how in the quantum mechanical regime light-matter interaction can be controlled. Can we capitalize on quantum optics, light-matter interaction itself, and engineered material properties? Can we actually change properties of matter to enable certain outcomes for our experiments to create a useful and exotic collective state? Now, I'll put useful and exotic because useful will be the quantum technology aspect of it. Can we do something with it? Because is it controllable? Is it tangible? Exotic is, can I make something interesting out of it, whether it's useful or not? Can it actually, physics-wise, science-wise, can it be something interesting? So this is effectively, it maps itself, this question maps itself to something in physics known as the central spin problem. This is, you have one red blob, if you will, and then many other blobs, red or not, but many other blobs in the environment, and they're all interacting whether you like it or not, okay? So that is, in the exact case that we're discussing today, for quantum dots, this would be one electron spin trapped inside a quantum dot, interacting with a large number of nuclear spins already in the quantum dot as well. So a sea of an ensemble of nuclear spins with one electron, and their interaction is kind of out of your control, and you don't control every nuclear spin separately. You might be able to access them through the electron. That's the question that we have. So to get to there, I always like showing this, and I think this is a good place to show this as well. I'll highlight two very important recognitions of how quantum physics did progress with experimental achievements. One of them is, we keep talking about these quantum objects, quantum devices. It's important to take a moment and realize that the first Nobel Prize to actually isolate a single quantum object was 1989. Demelt and Paul got it to be by being able to trap a single ion, right? And then Demelt changed his signature to include the trapped ion illustration as well. So if you pay attention, this is Paul's signature, this is Demelt's signature, this is the trapped ion illustration. So that dot in the middle is a quantum object, the first ever quantum object, tangible, seeable by eye, if you will. Before then, of course, all conversations were hypothetical, Gedanken experiments type things, or larger ensembles where we extract what individual particle is doing. These are the first experiments where we can trap a single particle. And to complement it, we have the very nice work from Sacha Roche, Dave Ireland, and colleagues on doing quantum operations on these systems, isolated ions, atoms, and what you can do with them. So I highlight these two as great achievements on the way to us colloquially talking about the quantum object as if it's something easy to achieve and it was always around. So here is a photo from Oxford. You might have heard of the place. This is the trapped ion that Demelt effectively drew out, conceptually at least. And that little dot is the quantum object, right? That's a single trapped ion, and that's a quantum object. You have to take a moment and appreciate that that is years and years and decades of research that went into being able to actually see an isolated single quantum object. And now we have many of them together, so we're in the era where we're getting spoiled by the fact that we can do this across many, many platforms. It is worth knowing, appreciating that isolating a quantum object is a big achievement. And there are many ways we can isolate quantumness in objects, in materials. Superconducting qubits, we talked about, single atoms, photons themselves are quantum objects, of course, spins, individual spins in materials. So the type of systems that we tend to play with a lot is the combination of these two. So it's actually a hybrid arrangement where there is a stationary qubit, a spin, linked to optical transitions that produce quantum light, so single photons at the same time. So spin and photons are linked. So when we talk about, remember that second option to beat proximity, it was light goes from one blob to the other blob. That's what you need. The hue around the red blob is the fact that it's able to emit single photons. And the photons are correlated with the spin left behind. That's the nice format for these systems. So what do you do with them? Practically, then we talk about quantum networks, interconnection between different physical systems. So these red blobs here now are gray mode, but each one of these, we have a little recipe of how to build these things, despite your choice of materials for implementation. You have to have the flying qubits that link these nodes. You have to have processor qubits, the actual definition of a qubit that does the operations for you and links to light. And then you should have local registers. You should have a dump memory where you do something, you park it there, and you wait for the other part of the network to continue doing things. And when it's time, you pull back that information, quantum information, and you process with it, you work with it. So this parking of information is quite key for networks. And typically, what it maps to in physical implementations, the photon is the flying qubit. We don't have a better one yet. It works perfectly well, so we like optically active systems. Spin does a great job when we talk about matter that we turn into, or materials we turn into quantum devices, controllable devices. So it usually is an electronic spin. And then the register part typically tends to be as what might be a good candidate, lends itself automatically to the only other available choice, and that is nuclear spins. So if you have nuclear spins in the material, this becomes isolated, therefore quieter systems, slower, but at least they will store information longer. So that's the spirit of it. So many physical systems are pursued by many around the world. This is a growing field, a very fast growing field. I only highlighted a few that I like, and it's purely subjective. There's absolutely no calculated way of saying these are the best ones, but I like these. So that's it. And I said, if yours is not here, that's the and more, it's all lumped under there. And the one that I will talk about today are, in fact, the 3-5 quantum dots, or the semiconductor quantum dots. So we have these material systems to work with. Typically, when you have something like a confined charge coupled to light, you have some control mechanisms. You can tune its properties through applying a magnetic field. You can tune some properties through electric field. Or you can apply mechanical tuning, you can stretch the material, you can play with it. And then on the optical side, you apply lasers, light, effectively, to control their optical transitions between ground and excited states. It's a very famous 3-level system representation. Or you do directly spin control through magnetic coupling, in exactly the way Pascale highlighted. And if I come back here, wherever you see tuning, replace it with fluctuations. If I'm able to tune something, that means it's prone to that field, to that application. That means if I don't apply the field, which I call tuning, something else applies that field. It's called fluctuations from my perspective, right? So the electron spin will be split by Zeeman if I'm applying an external magnetic field, that's tuning. But if background magnetic field fluctuates over time, the Zeeman splitting will vary over time. I will call that fluctuations, right? So if you're able to tune, you are prone to fluctuations. Or if you see fluctuations, that's good. That means you can control it to suppress in return. So I'm putting here a very, very rigorous graph, tongue-in-cheek. It's number of spins, this nuclear background spins, number of spins versus strength of the interaction, I classify as few and many. And then on the y-axis, weak and strong. Of the physical systems that we typically work with in material systems, you will hear spins in silicon, spin qubits in silicon or diamond. They map into this part of the world. There are few spins involved. One electron spin that we're interested in talks to a handful of, say, carbon-13 spin-active nuclei. So it's few. And that interaction is weak. It's dipolar. It's a carbon-13 somewhere over there. There's a distance. It's a dipolar coupling. So it's generally the weakest interaction that you have in the system. Spin waves in rare earth ions. This is weak interaction, but there are many, many of them at the same time. So it parks, that kind of a system parks itself over here. You get nice spin waves in crystals. You get the strong interaction in materials like hexagonal boron nitride, or this very nice system where there is the electron wave function overlaps strongly with only a handful of nuclear spins. So it's a 5-spin combo, 4 nuclear spins and 1 electron spin, very strongly interacting, but only a few in this case. And the semiconductor quantum dots have their space all the way up here. There are many, many nuclear spins, and they all interact very strongly. So it's a very interesting system. It's probably the worst system if you are picking a system to say, I want an isolated spin without having much effort. This is not an isolated spin. It's a highly coupled interacting spin system with very large numbers, but it's also fun. So, and if you do things in a nice way, you actually do benefit from the knowledge of the interaction and suppress the effects. So what is our workhorse that we play with? These are these small little islands. It's about 20 nanometers in size. They're very nano scale. 20 nanometers in size, few nanometers in height, so little pancakes of one material, indium arsenide, as Pascale also mentioned. Indium arsenide as one type of semiconductor, small island buried inside another semiconductor, gallium arsenide. The difference is gallium arsenide energy gap is much larger, so this ends up being a realization of a particle in a box problem. If you put an electron in there or hole, it sees walls, energy walls around it, so it can't really leave, kind of gets trapped. And then by applying electric field, we can tune that charge. It's both in terms of its wavelength, but also in terms of the number of electrons in the quantum dot. So it's actually a very nice device. If you put the electrical gates, these are the quantum dot layer. This is a highly doped layer. Here is your reservoir for electrons. By tuning voltage in the lab, you literally load 1 electron at a time. Coulomb propulsion makes sure that there is finite voltage ranges where there's nothing but 0, nothing but 1, nothing but 2 electrons in the quantum dot. So it's a very nice tunable system. You dial up your trapped ion effectively. Now in the case where we load a single electron like here, a single electron is loaded and that's it, then you have an energy level scheme, if you project it to atomic physics, that will look like this. The spin up and spin down of the electron is going to represent the ground state under a finite magnetic field. The excited state will be that same electron plus an exciton, an optical excitation in the system. And that gives you a nice 4-level system to work with. So this is an example of the device that we work in the lab with. We don't have cavities. We have a half-ball lens on top just to collect a bit more light. And this is the chip, the semiconductor chip. Inside, if you look carefully, if you zoom in from this half-ball lens, you see these contacts, these electrical contacts. And if you zoom in more, you see these individual quantum objects scattered around randomly inside the lattice. So it's the same concept again. One isolated quantum object, visible because it emits light 1 photon at a time. And then we take these systems and we play with it, essentially. So a quantum dot is a spin-photon interface. So first, the photon side. I called it optics because a lot of things are said about quantum dots, historically, legacy questions which have all been answered, and it's worth highlighting those. On the optics side, semiconductor quantum dots are the best we have across the board, across the platforms, across any physical system that emits light. They are the best ones we have. How? They are the brightest. They do have unity quantum yield. No other system actually gives us unity quantum yield in a material, hosted in a material system. It's a high Debye-Waller factor. That means most of the light goes in the transition you think you should be using, not in other lattice-engaged phonon-assisted transitions that are not useful for quantum networks. This is quite a high percentage compared to many others. The photons that come out are actually quite good. If you do the excitation correctly, the photons that come out are almost transform limited. In some cases, they are transform limited because they happen to be in a nice cavity, because it relies on the maturity of the material, the semiconductor industry for fabrication. So it's fairly straightforward to get, now I can say that, it's fairly straightforward to get it to transform limited photons without much effort. They are identical. So across the board, there's always this discussion about, oh, each quantum dot has a different wavelength. They are all identical because they're all electrically tunable or temperature or by other means tunable, and you can bring them all to the same color with a little bit of effort. So that's all doable. The tunability takes care of that. They can be electrically driven. You don't need optical excitation. You can get away with electrical excitation as well, which is an advantage in some cases. they can generate entangled photons from the get-go. They're not limited to a single photon only. They can generate pairs of photons that are entangled as an advantage. And integration into devices is, let's say, it leverages the state-of-the-art semiconductor technology that we have today. So it's actually, it has all these promises as to how good a photon emitter these systems are. So where's the problem? The problem is the other side, the spin. Photon-spin interface, I need both to be good. This is, again, leveraging from the very nice lecture, this is a Ramsey interferometry. You take the spin, now we're looking only at the spin properties. You take the spin, you initialize it, and then you bring it down on the Bloch sphere to the equator, and you let it evolve. And then you wait for some time, and then you bring it back and make a measurement to see how quantum it remains after some time. And what this shows you is that if you do nothing to the quantum dot, the electron inside the quantum dot sustains its coherence of order a couple of nanoseconds. Now this is a problem because the optical emission is of order 1 nanosecond, right? Now you can say, but we've seen in the lecture the spin echo compensates for these kind of fluctuations as well. You can do spin echo, and it does indeed compensate. It gives you microsecond range all of a sudden. So it's 1,000-fold improvement of coherence time by protecting it, doing simply a pi pulse. As the system evolves in the equator, you flip it and it comes back and everything refocuses. So it works. So coherence is implicitly there. It's just not accessible to you if you don't do that correction. You can say, okay, I protect the spin and I should be okay with spin echo or dynamic decoupling pulses. There is one problem. The problem is this is a spin-photon interface, and you rely on that photon to be emitted. It takes about a nanosecond or fraction of a half a nanosecond for the photon to come out. During that time, you can't do anything. You cannot protect the spin. You have to sit and wait. That's a very long time if your coherence dies of order 1 nanosecond. You have lost most of your electron spin coherence and how it's supposed to remain correlated to the photon that leaves the quantum dot, right? You can do whatever you want afterwards, but in the process, you get a cap of entanglement that survives between the photon and the spin. It will never be very good because the electron wanders off. So you got to fix this part, right? Even if T2 is good, spin echo works, the Ramsey interferometry is a good indicator of how good your quantum network will be if you were to build it, or how many of these particles you can weave out as new matter. So it comes from the fact that, again, the culprit is the nuclear spins. This is very strong interaction, and many of them at the same time. So this hyperfine interaction means nuclear spins wander randomly, and it causes an Overhauser field, a fluctuating field on the electron. Electron actually itself causes a night field back on the nuclear spins. So everything is dynamic. They're all turbulent in there. Nothing is quiet. And by light, you can actually polarize the electron spin, which in turn polarizes the nuclear spins. So you can control the nuclear spins by simply driving the electron in a particular direction. So one option is, if we want to quiet out the nuclear spins, if we don't want them fluctuating, you should polarize them all. That's one option. Polarizing them all, people have tried. It's great achievements. 70, I mean, even more now, I think, have been achieved of nuclear spin polarization. The problem is this. The Overhauser field is so strong, it's of order 7-8 Tesla on top. So it becomes impossible to call the electron a qubit anymore at that point. So it's actually terrible. It makes the qubit worse. Also, 70% polarized ensemble fluctuations are roughly the same as 0% polarization. Until you get to 95, 96, you're not going to see a significant effect. So it has to be a different option. Luckily, we do. So I'm presenting it as these are the indium arsenide quantum dot section, and these are the gallium arsenide section. This is what it kind of looks like, a sea of nuclear spins with one electron, big electron talking to all of them. So the Zeeman splitting that I'm supposed to magnetically couple, the Zeeman splitting is blurred out by this random fluctuating field in the background. So it's a time statistics or probability distribution, if you will, as Pascale highlighted. What is nice about this is that don't worry about that, but this kind of maps itself, even though it's bosons and fermions, it's a bit of a detail, it kind of maps itself conceptually to the idea of many atoms coupled together through a common mode. In this case, one cavity or photons. So this is the second option that we discussed, two red balls coupled by light. This is exactly how you realize it experimentally, and there are many experiments here as well. Very nice optical mode, commonly shared by many atoms. And you look at how the atoms interact through the common mode as opposed to proximity. In the same spirit here, the nuclear spins actually talk to each other through the presence of the electron. So it becomes an all-to-all coupled, Pascale highlighted that, becomes an all-to-all coupled system essentially to study. So instead of talking about a classical or semi-classical blurring of a two-level system, the actual picture, actually, borrowing from the previous example, is that you have many of these states very closely packed to each other. It's just that you're unable to distinguish which one is which. So therefore, the system you kind of randomly drive all of it together, right? So actually, it's not that there's only two systems, two levels that are fluctuating. You have many of these in this electronuclear ensemble, right? If there are 50,000 nuclear spins on one electron, you can think of it as one electron seeing semi-classical fluctuations, or you can think of it as 50,001 spins interacting, right? And that's the story here. So I'm taking that finely distributed quantum states and projecting it here. This is the three-level system that we have. We coherently drive the magnetic coupling through optics, through a three-level system, and we do readout by using the direct resonant excitations. And we effectively drive essentially spin-Rabi interactions. And here now I have a different definition. Each of these states have to represent the electron and the nuclear spins simultaneously. So the top one is the electron spin down manifold, and the bottom group is the electron spin up manifold. The electron spin is identical in all of those, but nuclear spins change by one value. So 50,000 we said, so 25,000 up, 25,000 down would mean a net 0. So IZ projection would be 0. But if one of you raised your hands, then it would be IZ plus 1. And it's so closely packed that it's very difficult to visually see in the optics emitted, in the light that is emitted. But that's the picture. I'm going to take that and rotate it so it matches more atomic physics description of ensembles and spin states, hyperfine states. So same idea, IZ over here, plus, minus, and spin down manifold, IZ over here, plus, minus. Now you realize this is about 50,000 states that way and 50,000 that way, right? So it's 1, 2, 3, 50,000 to 50,000. If all the nuclear spins were polarized, we would be at the far end, which one is positively polarized, then they would be all at the one end, one final state over there. If it's negatively polarized, all 50,000 of them would be all the way over there. In reality, we're around 0, and the distribution is roughly thermal. Thermal in this picture is hundreds of states. So when we talk about our quantum state for the electron, actually, for the electronuclear system, we occupy about 1,000 states, roughly, or many hundreds of states. So it turns out that when we do, this is the key part of it, when we do dynamic, three-level coupling to do magnetic drive, what we're doing is actually, it's a very simple picture. We are driving this resonance, but non-resonantly, we're driving this spin flip processes as well. So we're accidentally flipping a nuclear spin going outwards. But because this is also occupied, we're also driving it back in. And how far this resonance is actually not equal. So this is more likely. So when you think that you're driving this transition only, it's actually, you are driving that transition, certainly, but taking this state and flipping one nuclear spin to come back here is slightly more likely than taking this spin and accidentally pushing it away. The same holds on the other side, okay? Take my word for it that what the system does is it simultaneously takes the system. Even if you were in a single state, it would distribute it out. But if you were out there, it would distribute it back in. It's more likely to come back in. So what will the system do to a thermal distribution? As soon as you start driving, it will start to shepherd them in. It will start to narrow down that distribution so that the spread of nuclear spin fluctuations is reduced. So, and that's an example of what you're seeing here. If you look at this broadening, this blurring, directly measuring the electron spin resonance width, this is, the red is when you don't do anything. But when you do this process of, don't even look at the result. Let's just keep driving for some time. And then let's see what happened to the distribution. distribution looks much narrower. Distribution being narrow means this blurriness has been shrunk. It's reduced. So spin coherence should be longer. So if you do this experiment, the Ramsey experiment of oscillations, where we got only 1 or 2 nanoseconds, and compare it to doing this preparation stage, very simple 3-level drive that we had before, and compare the two, you get an order of magnitude improvement on spin coherence. Just by driving it, right? Just by changing that thermal distribution of nuclear spin projection along that axis. This is one of the first results that we had that showed electron spin benefits from a quieter background. Now we need to understand what quieter means, of course. Now if I look at these states and I look at this 15 megahertz that we measure here, the separation, energy separation from starting from spin up IZ to spin down IZ versus spin up IZ to spin down IZ plus 1 is 25 predicted. So that means this blurriness is actually in this limit. Now that we've cooled the ensemble a bit, we should be able to resolve those transitions which were blurred out in the past, right? We did say it's all blurry, but now that we know that they're finely spaced, if the fluctuations have been reduced, we should be able to see those states. And in fact, if you drive them over as a function of time, if you do Rabi oscillations, these are nuclear spin Rabi, the electron spin Rabi oscillations, and then these little features start to show up. If I do a line cut, you see these features coming out. So this is the electron spin resonance. Nuclear spins don't do anything effectively. Whereas these little peaks indicate a nuclear spin flip event. One of the nuclear spins flipped while we're driving the electron spin as well. But it's not a random nuclear spin flip. It's not like in this room. It's not like I say, Loic, raise your hand. So there is, in addition to everything being quiet, ground state, now we have one excitation, Loic raised his hand. No, what we have is you all raise your hands, tiny bit. If we add up all the arms, it adds to one arm, but it's actually spread all over as what we call a spin wave, and it resembles what we call the Mexican waves in football stadiums. You know, the hands just keep going around in a circle. It's kind of like that. So there's a bit of a collective phase associated with it. There's a collective excitation, essentially. So one nuclear spin equivalent excited everywhere. So what we can do now is we can prepare this narrowed down distribution, this cooled collective state, and then drive directly that transition. Not drive by accident, but actually drive that transition where we coherently try to flip it one nuclear spin. And then when we do that, these are the Rabi oscillations for an ensemble of nuclear spins, a collective excitation. They're also modest, but you do see the oscillations. And in fact, the oscillation rate, the Rabi rate, depends on how many collective coherent spins take part. Whether you polarize at 0 or you polarize at a positive value or a negative value alters this combination because how many spins take part becomes a question. So we are dealing with a collective ensemble. So for the first time, what used to be a decoherence mechanism for the electron spin now shows signs of collective coherence working together. So we can talk about collective states. So once we create the spin wave, a single nuclear moment equivalent, we need to make a measurement to be able to see it without actually driving it. So this width was around 25 megahertz, if you remember. 15-ish. The splitting we're aiming for is 200 kilohertz, so it's a very, very small frequency change for the Zeeman, for the electron spin. We want to do Ramsey interferometry, same, but we want to see how the fringes change, how the phase acquired shifts. So when we do that Ramsey interferometry, it takes us a long time to be able to sense a single Magnon, single nuclear Magnon, that's what we call them. But we are able to get to the regime of single nuclear spin detection in what is known as Allen deviation from engineering, but also precision quantum optics. Talk about clock transitions. So in the spirit of clock transitions, we're able to get to the regime where we need to be able to see the difference between one nuclear spin in the crystal being up versus not. Right? And this is the experiment for it. This is this is not the peaks that we saw before. Those are the populations, being able to see those magnons. Here, we're sensing them by phase. So there's a positive phase if the nuclear spin wave is upwards, and it's a negative phase, of course, if the nuclear spin is pointing downwards, because the electron senses it as a positive or a negative addition. But we're able to identify these transitions. Now, I threw in a few more states in here because we don't really have 50,000 identical spins. We have indium, we have gallium. It's actually quite a complex system in there. But we can sense a single nuclear spin using the electron as a sensor. There you go. That's the electron positive phase, and this is the negative phase for the two polarizations, two angles, identifying the polarity. So why do we do that? There's a reason for it. The reason is actually it's useful to be able to sense. And we don't need to know the result. By combining the cooling and then the sensing to see if the system has evolved to a positive or a negative deviation from where we thought we're going to be, we can combine it into an algorithm. And the way it works is you prepare the IZ value of your choice, you park it, and then you let go. You know that the system will eventually evolve, either to positive or negative, right? What you do is you let it evolve, and then let's say that it acquired a positive IZ, then you measure it with your sensor, with the electron. Ramsey acquires a phase associated with that. So it's imprinted. I don't need to read out, but it's imprinted in there. And then I do an exchange. I get the electron to talk to the nuclei. Hartmann-Hahn interaction, special name. Basically what it does is, if there's an excess phase in the electron, it maps it onto the nuclei. If it's positive, it flips it down. If it's negative, it flips it up. It's a PID, effectively. It corrects for the deviation that has been sensed by the electron. I don't need to see it. I don't need to know how much it deviated. I just don't want it to deviate. So we can use this as a sensor to feed into the exchange, and then we reset the electron and start all over again. So it's a corrector for any deviations you might have. And when we do this, this is the electron spin Rabi that you saw before, and these are the sidebands you saw before. And now if we include this algorithmic cooling on top, then it looks this clean. It all of a sudden becomes a neater system with the coherence time expanded now to 125 nanoseconds. So we go beyond the 100 nanosecond psychological regime for this. So this is roughly where we stopped. It's great, but as you can see, these are quite broad features. If I show this to an atomic physicist, there's nothing impressive about it. Atomic physicists are more used to the delta functions. So I need to work with something else. So normally in material science, strongly influencing what we do, there is a way. The way is to eliminate this inhomogeneous strain distributions to end up with something a bit more controllable. Usually when you go for a next generation, it ends up being some exotic material name, hard to pronounce, and say, turns out this very fancy, hard to find material actually has a much better property. Turns out, no. It turns out that indium arsenide in gallium arsenide is not the solution. Gallium arsenide is the solution. So it's even a simpler, more well-understood, more easy to manage system turns out to be the solution. In these kind of quantum dots, the droplet epitaxy method is used, where you etch out holes, you put gallium arsenide in it, in a matrix of aluminum gallium arsenide, and then there is no strain in these guys, and it's uniform. So you remove the inhomogeneity, the thing that broadened those peaks, the sidebands that we so desperately wanted to see. So when these are very nice dots, by the way. I'll highlight two results from Richard Warburton from Basel. He immediately took two of these quantum dots and showed that the photons are indistinguishable reasonably well without doing much effort. So these are good systems to work with. Again, quantum dot optics still wins, even if you change the material. And how about spin? And this is the other result. Immediately go into the algorithmic cooling to see what happens to the electron spin. You can extend it from, again, few nanoseconds only, because you still have 50,000 nuclear spins around, to around 600 nanoseconds. So for comparison, the spin T2 star of NV center in diamond with hardly only 1% nuclear spin active carbon around is about 1 microsecond. So with this technique, you're effectively creating almost a spin vacuum in a lattice where every single atom has nuclear spin, and not 1/2, 3/2. So every single spin has high spin, but yet you can quiet them all down to effectively have 1 to 2% effectively cool. So what can you do with this system? Immediately you want to look at that spectrum, right? So if its inhomogeneity is gone, those Magnon sidebands should be a bit better. And in fact, when you do, they are much nicer. So hopefully now atomic physicists in the audience can appreciate that this is a relatively homogeneous system, nice and clean system. That's your electron spin resonance. All of the first sideband we saw before was this hump. Now inside that large hump, you can resolve gallium and arsenic atoms, nuclear spins individually. Not only that, but the isotopes of gallium. So by optics, by light, you're looking at a quantum dot and seeing contributions of different isotopes distinctly from each other. There is no microwave involved here. It's only done by structured light. We write the microwave field onto the light modulation, and it's only light exciting the system directly. So it's all extracted by luminescence. So now comes the question, well, if I can isolate them and these are that narrow, can I do something? It's the last bit. Yes, you can. You can go back to the original papers that were written when quantum dots came out as a promising system to deal with before we knew anything about it. Very nice proposals. One of them was, can we use them as a quantum register? Can we actually take the electron spin, write a quantum state in it, and then transfer that state to a nuclear spin ensemble as long as they're quiet and sustain their quantumness? Can we then use it as a register? And that would be the algorithm. If you quiet down a select isotope, gallium-71, you prepare an arbitrary state for the electron, you swap it to the gallium nuclei, the Magnon mode, and then you wait for some time, and then you swap it back to the electron, and now the electron has that quantum state back, ideally. So you measure to see how well it matches what you thought you wrote, right? So it's a fidelity measurement to see how long can you store, and is it what you put, do you get back what you put in? And so this is two curves that you're seeing. The first one is it drops over some time scale, tens of about a microsecond, and then it drops again over 100 microsecond. And so if you go back to the electron and flip it halfway through, you're doing a spin echo on the electron. You're leaving the electron alone, so it does whatever it does. But if you flip it halfway and continue doing whatever it's doing, all of a sudden the coherence goes up. That's your storage time. You can store quantum information for 130 microseconds in the nuclear spin ensemble that used to be fluctuating like crazy. And here, I like this a lot because we always talk about the electron spin doing Ramsey to sense the ensemble, the environment. We keep talking about the nuclear spins as the environment. This is the reverse. We are using Ramsey on the nuclear spins to measure what happens to the electron. And the nuclear spin fluctuation, variation, is able to tell the difference between electron spin fixed to up versus fixed to down. So you can actually see the phase difference that nuclear spins gather. That's the night field, direct observation of the night field in return of what the electron spin imposes. So I'll finish off by many opportunities now that you have this engineered state to work with without having access to individual nuclei. You do have access to individual isotopes and elements, but also you get these tiny little features here that are kind of ignored. These features, this one, these ones, they're resonances at the difference frequency of the Larmor precessions. That's where the elements and the particular nuclei, the species, and the electron interact. But these are where combinations of species interact with the same electron. So those are the transitions, those are our gateways to inject correlations into subspecies. So you can talk about a symmetric or an antisymmetric state created by driving these states by accessing those transitions simultaneously to both subspecies. So there's a lot of work to be done in that direction to look at interactions between subspecies, not just nuclear spin as one entity, but many small interacting subsets. I'll finish by, actually I'll skip this, I'll finish by this one to say there are two routes now that we have done this. The two routes are, we have an interesting physical system to play with. We can go the more applied way, and we can continue working on information storage and turn them into useful devices. And then we can also go in the basic sciences, the fundamental concepts way, and look at how this interesting system evolves and interacts with its subspecies. One thing that we're working on right now, for example, is the concept of a many-body singlet state. A singlet state is one electron up, one electron down. You don't know which one is up, which one is down. It's a beautiful entangled state, but the net spin is 0. Even though you have 2 spins, the combination is 0. Imagine 50,000 nuclear spins in a fully coherent quantum state where the net magnetization is actually 0 in any direction. It's like almost they disappear. So that's one of the directions we're heading. And I'll finish off by thanking you and enduring me today. Thank you very much.